artificial intelligence will completely transform our world. But what is AI? Why will it affect you? And how can you and your business survive and thrive through the AI revolution? Welcome to AI and You. Here is your host, author, speaker, and futurist, Peter Scott.
Hi, this is episode 193, and my guest today is Rachel St. Clair, CEO of Simuli, which she co-founded with Ben Goertzel, who was on the show in episodes 106 and 107, and who coined the term artificial general intelligence, or AGI. Simuli is working on advanced neuromorphic hardware designs to create very power-efficient AI with AGI as a goal. Rachel is a fellow of the Center for Future Mind, with a doctorate in complex systems and brain sciences from Florida Atlantic University. She researches artificial general intelligence, focusing on complex systems and neuromorphic learning algorithms. Her goal is to, quote, help create human-like, conscious, artificial general intelligence to help humans solve the worst of our problems. All heady stuff that is coming to a boil with today's huge advances in AI. We'll get technical at times, with Rachel referring to terms like LSTM, which just stands for long short-term memory. But all you need to know is that it's a kind of artificial neural network design that preceded the transformer, which is the basis for ChatGPT. Let's get right into the interview. Well, Rachel St. Clair, it's a pleasure to have you on Artificial Intelligence and You. And we've just heard a description of what you do, but I'd like to get that in your own words because it is such a nebulous subject to wrap one's brain around that I'd like to hear this from your mouth directly. Tell us what exactly you do.
Yes, awesome. Thanks for having me on here, Peter. And I run an AGI company, and we're focused on building kind of more infrastructure and frameworks to help accelerate this new wave of what it means to be a more intelligent AI system than what we currently have. And so we're quite focused on resource-efficient methods of computing and along the path to AGI, which is a pretty big goal, pretty grandiose goal. We've demarcated some very good stepping stones that we think will just revolutionize different pain points in tech. So compression, data storage, things like that on the way to AGI.
Thank you. And I want to back up a few steps here because you're talking about this as a product that is on the way, assured, and to most people, I think the question of whether AGI is even possible is an open one. And so perhaps we should start with some definitions of artificial general intelligence, which your colleague Ben originated the term of, but it is a famously hard one to pin down. And for the purposes of what you've just been describing, the target you're aiming for, what is AGI?
Right. So you are correct in that it's famously difficult to pin down. I think it's up there with consciousness, maybe not as difficult, but it seems to have a revolving target, right? As soon as we get close to it, we say, well, that's not quite it. So as a metaphor or analogy, I always like to say that it's like data from Star Trek, right? If you're familiar with the Next Generation Star Trek.
Yes.
And if for people that aren't, what I'm after, what I'm looking for is a way to have something compute that is in the realm of human understanding, right? And that's a little nefarious. Let me unpack that if you would, right? So I want the computer to be an entity, its own entity, to have self-awareness, the ability to think on its own and to really understand in a similar way that we understand. But I also want it to be better than us because I can go make another baby, right? I can go make another human. I can make something that computes the same way I do, right? But to do that in a machine, the real advantage is to have something that can help us with our deficits, help us with where we lack in our logic and our emotions and understanding and things like that. And so that's the sort of AI that we're really after at Simuli, right?
Right. And so I think that gives us a good idea of what you're going after. But that's incredibly ambitious. I mean, that is out of all of the spectrum of descriptions of AGI that I've encountered, one of the furthest out ones, I would say, in terms of its attainability.
Well, I'm not so sure. I'm
Okay,
sorry, Peter.
go
I'm
ahead.
I'm not so sure because if we think about OpenAI and their chat GPT, I mean, everyone has to bring this up in these conversations nowadays. They've achieved some level of that, right? They have something that works with human language and fills in a lot of our deficits on human language, right? If you ever used it to compose an email,
Hmm.
sometimes it's really pointed out to you, hey, that, that grammar is not correct, or that could be interpreted a wrong way if you're not careful with your wording. So there is some level of this ability to point out to ourselves, what we might be missing in our thinking. I think that it is difficult and it is an ambitious goal. I'm not disagreeing with you. I just don't think it's so far away from the direction that we're all heading towards in the AI field.
Right. And there was a paper by researchers from, I believe, Microsoft and Google saying that GPT-4 was showing signs of artificial general intelligence, again, by certain criteria. So, what criteria should we use to determine if AI is AGI?
I think that's a challenging question, and I think it'll continue to evolve as we get closer and closer. One of the big things, kind of the hallmark criteria, is that it should be able to learn within reason anything we can learn, right? Anything we can learn, it should be able to learn too, within a reasonable amount of data and resources. So for us at Simuli, that's a big caveat there that often gets overlooked is the resource constraints, right? Of course, you could take anything, any Turing machine, and it could learn anything over infinite time scale, right? But that's not incredibly useful, right? Or Marcus Hutter's AXI, right? Wonderful framework, wonderful theory, but computationally intractable. So we want something that has some sort of similar resource usage as us, which might be an indicator that it's learning in a similar time scale that we're learning. And when I say time scale, I mean within resources that we have to put at it. Of course, it's going to be much faster because electronic circuits compute faster than human neurons do, right?
Right. Do you have some kind of internal goal, milestone, benchmark, like if it can do this, that's step one, that's our marker?
I think it's several things. It's not just one, right? Because that is the general nature. Otherwise, it would just be AI, right? So it's several things. So I think doing complex things like fully automated self-driving without having to be taken offline for training. So for me, it's less about the exact task, right? Because you can make any model achieve almost any task, right? If you put enough effort and resources into it. It's about the number of tasks it can do and what it's going to take to do those tasks. So how much resources is going to take? Do you have to train it on streets in Germany? And then when it goes to streets in Africa or streets in the US, you have to take it completely offline and rebuild its whole brain. To me, that's not an AGI. I want to not have to rebuild its whole brain. I don't want to have to restart the inner workings of the model and retrain and give it copious amounts of new data to be able to extend its learning to something quite similar, or to extend its learning from one situation to another situation where there's a shared principle of, say, something like gravity. So, what we're looking for are these kind of really deep concepts that we see in humans and animals, concepts of composite tool use, right? That's something that humans are remarkably good at and other animals not so much. Things like being able to adapt and share concepts between distantly related tasks. So, as an example for that, one of my favorite examples is if you talk about Siri in your phone. So, Siri is run by something like an LSTM model, it's a type of AI model. And we also know these LSTM models can be pretty good at training on the stock market and learning to make trades on the stock market. But if you take your Siri model in your phone and you ask her to learn the stock market, she will forget everything she knows about language and she won't be able to return to that task, right? So that's kind of an example of how could you switch from one task to the next without reconfiguring the entire brain. Well, if you could take Siri and get Siri to trade on the stock market and Siri would still understand language, that
Right.
would be an example of a hallmark task for me. Does that make sense?
It does. And you're given a lot to react to there. I would like to say that you'd have to replace a large part of my brain before I could drive in Paris, let alone Rome or Bangalore. So I think you've set a high bar there. You got into robotics there, and I wondered about the question of embodiment, because the large language models have never been embodied whatsoever, don't use any machine vision. You have GPT-4 plus vision, which can look at things and interpret them, but it has not been trained with any reinforcement learning on manipulating objects in the real world. And you went to discussing being able to learn to drive a car, which may require a great deal amount of physics. And so does that require a different learning path than what's been put into large language models where they're trained on enormous amounts of text, but no embodiment?
Yeah, I think it does. And I think embodiment is going to be really important. It's not clear yet, and we're going to let research and testing inform us on the direction there, on our path there, exactly how much embodiment is needed. But from my understanding of how it's done in biology, which isn't exactly the way it needs to be done in computers, right? We're dealing with different substrate, different mechanisms. But we can take some good lessons, right? We've seen it done once, which means we might be able to infer some things about how to do it again in computers, is that you have this perception action loop. So you perceive stuff, you build your mental models, your concepts, you define your conditions, you detect what conditions you're in, and then you select behaviors. You select behaviors based on what states you think you're in. And those behaviors in turn change the environment, change the conditions that you're in. You turn up the thermostat, it gets warmer. You turn it down, it gets colder. Very basic stuff here. And so I think that loop needs to be for anything that's going to be able to kind of meander from one domain of knowledge to the next. It needs to be able to understand what it means to live in the physical reality. And if we really want something to understand us as we understand ourselves, it's got to understand some basic physics. And hopefully it will understand those physics better than we do, so it can help inform us, kind of be like a ChatGPT version of Einstein or something like that would be wonderful, right? Bring back some of these wonderful scientists and kind of help us progress even further. But I do think embodiment is something that's missing. The degree to how closely the embodiment needs to match our own, I think is still up for debate, right? And I think that's something that we need more research on. We need more papers on, more literature, more experiments, more testing.
So human beings take years of training to be able to deal with the real world. Do you anticipate a training phase that is equally rich?
Yeah. And I think what we have now is even, I don't want to say worse, that's not the right word, but we need less data than these AI models need, right? We need less time. If you were to compare, if you were to bring it down to the same scale on how long a synapse takes to fire in a brain versus how long one backwards pass update happens in the back propagation step of an AI model, or however you want to make your equivalents, right? There's big arguments on how equivalent these things are. AI models take considerably more resources, even if you just look at the power management, how much power it takes to run these models. I mean, it's millions of dollars to train things like ChatGPT, millions. And humans, I mean, children are expensive, people are expensive, but not near as much resources go into training people as they do to our AI models. So I think there's already this giant disparity in what it takes to learn. And I think if we can try to close that gap, we'll start to get closer to AI models that are way more like humans than just these super computational machines, which have their own place in the world, which have their own utilities in the world. But it's not the kind of AGI that we're particularly interested in.
I agree with most of that. I want to push back on the comparison of the training mechanisms, because human beings do take years of training, crawling around, putting things inside of other things, going to school, for a decade, and then more if you want to get even to the level of GPT-4 in its ability to pass the SAT. So I think there's a huge training phase there that we're not doing the same way. We get GPT-4 to learn how to do what it does in 2 weeks of an enormous power expenditure on 1 trillion words of text. But that's 2 weeks versus a human being doing 12 years. And one of these is not like the other. So we've gone in a completely different evolutionary path towards intelligence, it seems to me.
Yeah, I think that's a good point. And I think let's just look at power, right? The power requirements for training an AI on the same task of training a human are exorbitantly more for the AI, right?
Right.
If you just talk about how much watts of energy are used in the human brain versus are used in these AI models. And it's a hard comparison to make. And I think that's why there is no kind of hard, fast literature on it, because you got to make a lot of kind of assumptions on your comparison. Is this really like this? Is one backpropagation update really the same as a synaptic change? And you're comparing the human, which is very general, can breathe, can self-regulate its immune system, do all these things internally, can also do all these different tasks, to the AI model, which can do language, and which can far exceed the capabilities of language in a human. Right, so that comparison is difficult to make. So maybe that wasn't a fair example for me to use. I could agree with that. I think overall, I don't think it scales up. But I don't think it scales up when you look at how many neurons are in ChatGPT versus how many neurons are in, say, Alex the Gray Parrot, which was very good at language, could do some color tasks, had some emotional readings, could fly, could eat, could do all these different things, could speak bird language still, as well as human language. I don't think, we're getting as much out of these models as we see in biological counterparts for the amount of resources being used. But it depends on what you're looking for, right? If you want a super amazing, better than human language model, maybe you don't want to take my approach, because I'm very bad at spelling personally. And you would not want my capabilities in spelling in your chat GPT. That would not be great for you. And even though it still makes mistakes, on average, it's usually quite better. And same with self-driving, right? Self-driving makes way fewer mistakes than human drivers, right? But maybe we don't want it to be like human drivers. Maybe we want it to be zero mistakes. I don't know. I mean, that's more of a political and philosophical question. What degree of accuracy do you want your model to use? Do you want it to be more like an expert, or do you want it to be more like a general learner? And I think that just depends on the application. But for our purposes, what I'm really interested in is the general learning, the thing that is fallible, does make mistakes, is like humans, but, has a smorgasbord of applications it can apply itself to, a smorgasbord of things that it can draw new ideas and be creative on and provide empathy and understanding and all these extra layers and dimensions of humans that I think is rich and important.
You're talking about applications there, and your earlier example of the AI that's trained to do one thing, that Siri is trained on text and language, but if you ask it to do something else, like learn to play Go, it will forget what it learned about language. Same kind of model, but the retraining wipes out what it had previously learned. And so that's getting at the application of AI at the moment is ANI, artificial narrow intelligence. We have each one of these things can be better than human beings at one thing, but not do one of the others. And I think that in human beings, we also switch between modes. Like, for instance, ask me to solve a math problem, I engage part of my brain that's doing symbolic processing that's nevertheless layered on top of this neural network. Whereas with a large language model, if you ask it to do math, it doesn't, without special programming, distinguish between that problem and the one of make up some text that could be interesting at this point, or commonplace, the autocomplete function. So we human beings are naturally switching, and I wonder whether there is a model here of how to switch between different types of problems that human beings have solved, or whether you think there is some underlying unified field theory of intelligence that can do all of these, and that is your eventual goal.
It's a really good question, Peter. It's a really good question. And I think that we need sort of this in-between structure. So what I love about these large language models is they rely on huge vector spaces, right, to encode knowledge. And something similar is happening in biological brains, right? We have these large spaces which categorize constructs or define constructs of information. And one of the things that we've done in biology, or evolution has done in biology, is make this a hierarchical process. So you have these kind of nested constructs of information, right? So in vision, you have Gabor filters and lower levels of vision, and then you build these up to richer concepts like edges, shapes, colors. You build those up into bigger concepts. And somewhere in this large space of synaptic firing, we remove ourselves, the information is removed from the lower level perceptual distinguishes, right? And we get into these kind of larger, rich concepts where gravity is informed, the concept of gravity is informed by multiple perceptual senses, right? So you not only have vision, but you have auditory senses, right? So your understanding of 3D space or gravity or deeper concepts such as those are informed by multiple senses and inputs that you get in. And I think things like GPT and other models, DeepMind has some interesting models that have tried to kind of create this hierarchical vector space. Those are really interesting to us. And our own models like to play in that space of, okay, how do you organize information in a way that is building from your inputs, so it's tied into the lower level natural feature space of the world, but also bringing it out of this core perceptual feature space into deeper concepts. And those deeper concepts, I think, is what allows us to switch between tasks, right? To switch and give knowledge. This is that a priori knowledge that you would need to really bootstrap new applications when you're switching from one domain to the next. So you can throw out some of the lower level perception stuff when you're switching, doing a big jump into information domains, but you still need to retain these kind of core concept models of the world. So I think the answer is in between. It's yes, these are good, but we're not quite there.
And it certainly was a challenging question. You're talking about vectors there, and for the benefit of the audience that's perhaps not familiar with the technology there, can you explain hypervectors and dimensionality as it relates to the AGI space?
Yeah, so hypervectors is a special word, and that's at Simuli, we spend a lot of time looking at hypervectors. Hypervectors are different than normal vectors. So if you look at Simuli stuff, you'll see the word hypervector all over the place. And these vectors are large dimensional buckets of numbers. You can think of them as buckets of numbers, okay? So if you take a piece of string, a very long piece of string, you could cut up that piece of string. Okay, this centimeter of the string is this number. This centimeter of the string is that number. When your string isn't that long, we call them normal vectors. So this is a very kind of laissez-faire explanation, so don't take it too rigorously. But most AI models use vector spaces, and especially large language models, they use these vector spaces. So they have about 3 vectors or 3 strings of numbers that can be varying lengths depending on the type of model. And those vectors, the numbers change. And how they change and how the numbers relate to the other numbers and the other pieces of string, that informs the model how it's going to make its decisions and how the information is stored. And if you make those strings very long, you get into what's called hyperdimensional space. Very fancy. It's a bit hard to explain, but perhaps the best I can do for you here is if you think about a disco ball, it's got all these little tiny squares of mirrors around the surface, and that all those squares relate back to the center of the disco ball. That's the origin. So you can say that there's a line that goes from the middle of the ball out to each mirror. That's basically a vector. And let's pretend that your disco ball didn't have to be a sphere. The disco ball could be any shape. And depending on how you arrange those little mirrors, you now have some geometric shape, you have some geometry involved that you can use with various series of interesting maths to learn about the different positions of the mirrors in relation to each other. And so if you were blind and you were inside this disco ball and you had to like go and touch each mirror, you could figure out what shape it is. You could say, oh, it's shaped like a llama. This disco ball has information about llamas. So hopefully that kind of gives some intuition on how these models and hypervectors and vector spaces can encode information.
Right. It's a good introduction to the abstraction of these things that are thrown around. We talked on the show a long time ago, actually, about Word2Vec, which was the now more than 10-year-old model for encoding language as vectors, showing how close words were in different contexts that it figured out. So it would, for instance, know that king and queen were related in the same way that man and woman were. And at that level of simplicity, are we talking about the same kind of vectors?
Yeah, it's very similar. Exactly. So we take that a step further and we work in hypervector space, which says, okay, forget these simple constructs of king and queen, and let's apply these to these deep abstract concepts. So we're creating abstract conceptual spaces for these models. And so you can think of this, it gets quite technical, but it's quite similar. We're just making it more abstract. So another good analogy, it's easier to talk in analogies instead of getting into the deep technical stuff if it's not a technical discussion. If you have an abstract artist that paints some sort of Van Gogh or something like that, some very abstract art, you're at the museum and you're looking at the painting and you think, I think the artist was angry when they painted this. And suddenly the artist is behind you and they come up behind you and they say, no, actually, this is jealousy. And then you go, oh, okay. And so you update the way you interpret the abstract art. And the next time the artist paints a painting and you get a little bit closer to nailing down exactly what that artist meant. And they're behind you again and they tell you again, no, it's this. And that's kind of how the human brain works, right? You have this condition, detection, definition that is creating this abstract concept space of how information lives from the natural world, right? So you pull in information from the natural world that gets embedded in this vector, geometric, hyperdimensional space. And then another part of your brain figures out how to interpret that. And through a series of, learning, reinforcement learning, other types of learning, you learn to interpret better or worse what your brain is actually experiencing in the natural world. And that's hopefully you're starting to pull together all these different concepts that I've kind of brought up about deep conceptual spaces and abstract vector spaces and how that relates to actually interpreting and learning and applying different knowledges to different tasks.
Wow, so much to touch on there. That's the end of the first half of the interview. We're splitting it up like we usually do because we end up talking longer than many people would care to listen. In today's news, ripped from the headlines about AI helped in the search for love. Alexander Zhadan, a Russian programmer, automated his search for love using a ChatGPT-based chatbot, which interacted with 5,239 girls before finding the one. He decided to create a dating bot based on the ChatGPT API. The bot selected suitable profiles in the Tinder app based on certain criteria. For example, having at least 2 photos in the profile, chatted with them, and if all went well, suggested meeting in person. In total, out of the 5,239 girls, Alexander selected 4 most suitable ones. Ultimately, he chose one of them named Karina. Alexander said that the bot, quote, messaged me when the conversation with her heated up. In one of the conversation summaries, the bot directly suggested Alexander propose to Karina, which he did, and she said yes. 2 months before the proposal, Alexander told Karina about how exactly he used a chatbot. Quote, she was, of course, shocked, but in the end she began asking questions about how it all works, how it reacts to different scenarios, etc. And now we've been living together for more than a year, end quote. In the first year of this podcast, I was pointing out incidents that demonstrated how AI was penetrating the mainstream, and this would fit into that category. But there again, I think the last 15 months have tossed AI feet first into the mainstream, and at this point I'm just putting out reports like that one for novelty value. But why not? Maybe it'll give you some ideas. Next week, I'll conclude the interview with Rachel St. Clair when we'll talk about the role of sleep in human cognition, AGI and consciousness, and penguins. That's next week on AI and You. Until then, remember, no matter how much computers learn how to do, it's how we come together as humans that matters.
That's all for this episode of AI and You. Please leave a rating and comment and share with your friends. Get the book Artificial Intelligence and You and see more videos and articles at aiandyou.net. That's aiandyou.net, where you can also send us your questions. Thank you for listening.